Bill Shatner, and I've been learning about robots. Yes, robots, and particularly about the very important part they play in industry. I want to share with you some of the things I've learned. Now, the science of designing and building robots and the productive use of these modern-day machines is called robotics. Robotics. Let's get on with our story without...
Mr. Shatner. Mr. Shatner. May I have your autograph, please?
Isn't that cute? This little character wants my autograph. You know, when most people think about robot, they very possibly visualize something like this one. Or maybe a larger edition of the same thing. Here you go. Okay, little guy. Thank you.
Thank you.
In the trade, robots like that are usually referred to as personal robots. They're amusing, they're entertaining, and they can be programmed to do a number of useful things around the house. Program, that's the key word, and you'll hear it a lot today.
7 minus 6.
But this type of robot is already playing a much larger and more important part in education.
That is incorrect.
Computer and microprocessors are not new in the classroom, but when a programmable educational robot is added, the study of computer science takes on a new perspective. Ideas are transformed into action.
Your answer for 11 minus 7 is 4. You are correct.
But that's an entirely different story. We're going to talk about industrial robots, the steel-collar workers of today. And we'll begin right over here with a robot that meets the most often used and very official-sounding definition of industrial robot. Are you ready for this? Industrial robot. A reprogrammable, multifunctional manipulator. There's more to the definition of industrial robot, but that'll do for now. All right, buddy, let's hold it, please. Industrial robots come in a wide variety of shapes and sizes. This is a typical computer-controlled robot with 6 different movements or degrees of freedom. Some industrial robots have fewer degrees of freedom. A few have even more. Okay. The first degree of freedom, the arm sweep. It's like turning your whole body when you want to reach something that's directly behind you. Second degree of freedom, the shoulder swivel. Here's the third degree of freedom, the elbow extension. The fourth is pitch. And the fifth degree of freedom is yaw. The sixth degree of freedom is roll. pitch and yaw and roll together. That's like the human wrist, right? And there is where the end effector is attached. End effector, that's the term used for whatever tool is to be fitted, depending on what the robot is required to do. Now, that tool, that end effector, could be a riveting gun, a screwdriver, a welding tool, a cutting torch, an inspection device, an adhesive applicator, a laser gun, a paint sprayer, even suction cups, so that the robot can handle flat items such as sheets of glass. To this robot, we have added a standard grasping device, an end effector. It might be used in an assembly operation, or to load or unload a machine tool, or it might be used to fetch the fire extinguisher. Thanks, but no thanks. Body, swivel, shoulder, elbow, wrist, hand. What other comparisons to our human anatomy do we have? Well, the power supply for this all-electric robot's motors and relays and feedbacks could be compared to our human nervous system. And if our robot can be said to have a brain, it's right there in the cabinet housing the computer control system. Everything the robot has done was previously programmed right there. Okay. We're ready for some examples of robotics in action, such as the installation of electronic components in circuit boards. This integrated industrial system includes 3 robots, each one programmed with its own tasks, and each one synchronized perfectly with the conveyor. At the end of the line, the population of each circuit board will be complete, with automatic inspection included. And, on the subject of inspection, just watch this next robot get things in gear. It will install 3 parts, like this one, in a sub-assembly. But first, each gear must pass inspection. Gear number 1 is okay, it goes in place. Gear number 2, it also passes inspection and gets installed. This? A defective part? Down the drain. Get another number 3 gear. Inspect it and install it. And finally, let's give it a whirl. Now, those robots weren't working alone. They were programmed to work with other robots and with conveyors and even with inspection systems. A further step is for the industrial robot to interface with other kinds of automated machines. For more about that, we'll visit the National Bureau of Standards. The scope of this busy bureau in the fields of research and testing is very, very big. One part, the Automated Manufacturing Research Facility, is designed to help manufacturers improve productivity and quality through better use of automated machine tools and robots. A principal aim is to standardize the control systems, the links between robots and other automated machines, so they operate together as one unit, a workstation or cell. Let's take just 1 minute for a simplified overview of an automated workstation in operation. There are 3 principal units involved: an automated cart, a vision-equipped robot, and an automated machining center. The workstation has been ordered to make 1 copy of a dovetail metal box. All the blank parts are delivered by the cart. There's no human hands involved. The only person you'll see is a research engineer keeping tabs on this experimental project. we'll just take the time to machine the top of the box. There's no need for a step-by-step description, but I think it is important to talk briefly about how it works. What we're observing here is data-driven processing in action. All the information necessary to build this box is stored in a database. We cannot see or hear computers talking to one another, but hundreds of messages are being exchanged as the activities of the materials handling workstation, which controls the cart, and the horizontal machining station with its attendant robot are coordinated. When both sides of the box top have been machined, the robot moves to the blank parts tray for the second piece to be processed. That robot was vision equipped, and that's how it was able to pick up the right part at the right time. The Bureau of Standards has done a lot of work on robot vision. Let's have a look. This flash-equipped robot vision system is certainly not related to eyesight, the way you and I experience it, but a method whereby the picture of an object is instantly converted into a grouping of binary numbers, and the robot has been programmed to separate the round cylinders from the rectangular blocks. The blocks go in one row, the cylinders in another. It seems to me that the industrial applications of robot vision in, say, parts sorting, or in precision assembly, or in critical inspection, why, they're almost unlimited. A practical joker at work, but the vision-equipped robot's search and find program prevails. Our seeing eye robot isn't fooled for long. How about a sense of touch? How about equipping our robot with tactile sensory devices so it can tell hot from cold, or be instructed to grip firmly or very, very gently? Built into this gripper mechanism are sensitive areas that feed back pressure information to the robot control. And yes, that is a fresh, raw egg. If there's any doubt in your mind, well, scrambled egg, anyone? Well, now let's get back to the serious business of the steel collar worker, the industrial robot, and the many things that it can do. Whether it's materials handling or a relatively simple pick-and-place application, or the most critical vision-assisted assembly task, or machine loading, or welding, all kinds of welding, or soldering a tiny circuit board with watchmaker's precision, or laser beam cutting, or a TV-monitored multi-stage inspection process. The list of tasks that industrial robots can do, and do superlatively well, is growing all the time. And the manufacturing engineers, those production line specialists, they will be the very first to tell you that the robot's #1 job is to work in conjunction with other equipment. That robots in industry are just one of the elements that make up an automated single machine workstation, or one of these more extensive systems made up of several machines and robots working together. Whatever the job, the robot is at its best when it is a fully integrated part of a workstation or work cell. Speaking for myself, I'm impressed. The assembly of an automobile engine, done efficiently, done accurately, and automatically, right to the point where the completed engine is ready for delivery to the factory floor, and robotics made it possible. What kind of an act have we got to follow that one? Easy. Let's build the whole automobile. This automobile assembly plant boasts 2.5 million square feet of floor space. You'd never know it because just about every foot is crowded with equipment devoted to the production line. Platoons of our robot friends help turn out about 1,000 new cars each and every working day, with capacity for a whole lot more whenever needed. There's 10 miles of conveyors, and if it's more robots you're looking for, here's some of them right here. About these robots, there's something we need to think about. It's been said that robots today are just about where computers were quite a few years ago. At that time, many were concerned. They felt that the rapid rise of the computer would result in mass unemployment. It never happened. And there's concern today. Do these robots pose some kind of threat to human employment? Robotics seem to point the way toward increased production and improved product quality without corresponding increases in manufacturing costs. Now, that's true. It could lead to a very real improvement in the overall economy. And if that should come to pass, why, there ought to be more employment opportunities in that expanding economy, not less. And speaking of what lies ahead, what about the future for robotics? There seems to be no limit. Let your imagination run wild. How about intelligent robots? Artificial intelligence. Human-like intelligence functions for robots such as learning, adapting, reasoning, and self-correction. They're here today. They'll be commonplace tomorrow. As for me, I'd rather think about today, about how robots are performing boring, endlessly repetitive assembly work, how they're working with toxic chemicals, and in paint booths, neither place a particularly suitable environment for a human being. How they're relieving us of many of the hard, hot, heavy jobs, and the dirty and often dangerous work that not many of us ever really want to do. So what can robotics really mean to us all? Well, it can mean freedom from drudgery. It can mean increased productivity and better quality, leading to an improved economy. And maybe that implies an improvement in the human condition. Perhaps robotics can lead to a better life for all of us. I know what I think. How about you?